Hello and welcome to lecture 41 of the course Theory of Computation. Right. In the previous lecture, we saw many undecidable languages and from reductions using reductions from ATM. Right. In particular, we saw two undecidable languages, ETM and regular TM. Right. So ETM is the question. So given a Turing machine, does this Turing machine is the language recognized by this Turing machine the empty language, right? That's what ETM is asking, right? Given a Turing machine, does this Turing machine recognize the empty language, right? And regular TM is, given a Turing machine, is the language recognized by this Turing machine regular, right? So these are the two languages that we saw last time, and we saw that both of them were undecidable, right? So one way to look at both these problems or both these questions is like you are given a Turing machine and you are asked whether the language recognized by this Turing machine satisfies some property, right? So in one case we are asking, is the language equal to the empty language? In the other case we are asking, does this language belong to the class of regular languages, right? So we can ask many such questions of similar type. Given a Turing machine, does the language recognized by this Turing machine contain only strings of odd length, right? So that's a question, right? So this is a question that is specific to only the language of the Turing machine, right? So I'm not asking about other things like how many states does it have, or how the transitions happen, or is there a state where it loops, or anything of that sort. The questions that I'm talking about are only specific to the language. So once again, the question that I'm talking about is, given a Turing machine, does the language recognized by the Turing machine contain only strings of odd length, right? Another similar question is, given a Turing machine, does the given Turing machine accept at least one palindrome string, right? So palindrome is a string that reads the same way from left to right or from right to left. Another question that I can ask is, given a Turing machine, is the language recognized by this Turing machine, is it a finite language? Does it only accept a finite number of strings, right? So that's another question. Or does the given Turing machine accept a specific string, let's say 1011, right? This is another question, right? Because so again, we are asking whether 1011 does it belong to the language recognized by this Turing machine? So all these questions are questions specific to the language recognized by the Turing machine, right? And so we saw two questions in the previous lecture, and we saw that both of them were undecidable, right? ETM and regular TM. What Rice's theorem says is that all these questions that I've listed here, all of them are undecidable, right? So this is actually not covered in the textbook per se, but it appears as a problem. And I think the solution is there in the book itself, but it's not given in as much detail as any regular content of the text, because it just gives a solution, not much of explanation, right? So the Rice's theorem states that all these are undecidable. So given a Turing machine, if we want to ask, does the language recognized by this Turing machine, does it satisfy a certain property? The answer is going to be almost always this is undecidable, right? So given a Turing machine, it is undecidable to determine whether the language recognized by this Turing machine satisfies a certain property, right? And I say almost always and not always, because there are some minor cases where there is an exception, right? So these are going to be very easy to figure out, right? So let us just now formally go to the statement of the theorem, right? So we have, hopefully this gives an idea of the informal understanding of what the theorem states, right? So given a Turing machine, we are asking, does the language recognized by this Turing machine satisfy a certain property? And to determine this, answer to this is undecidable. So what do I mean by a property? Right? A property is nothing but a subset of Turing recognizable languages, right? So for instance, being regular is a property, right? So not all language, like only some languages are regular, right? So that's a property. Being finite is a property, right? A language is finite if it has finitely many elements, right? And we say that a language L has property P, right? So property P is a subset of languages if L belongs to that property. We also say that the Turing machine itself has that property, right? So we say that M, the Turing machine M also has that property. So instead of saying the language recognized by M has that property, sometimes we may say that M has that property, right? So the language recognized by M has this property, right? So give some examples. So one I already said, the set of regular languages is one property, right? So and we saw in the previous lecture that to ask whether the Turing machine satisfying this property is undecidable. Another property is set of all languages whose members are only odd length strings, right? So set of all languages whose members are only odd length strings, right? So this is the same as this question, right? So this question is asking the first question that is listed here. It is asking whether the given Turing machine satisfies property P2. That P2 means P2 is a set of all languages that contain only odd length strings. So the question here is, does the language recognized by the Turing machine contain only strings of odd length, right? P3 is set of all languages that contain at least one string that is a palindrome, right? And P3 is the same question asked here, right? Does the given Turing machine accept at least one palindrome? So maybe I'll just note it down here. So this is asking, does the given Turing machine satisfy P2? This is asking whether the given Turing machine satisfies P3. And P4 is a set of all languages that contain 1011, right? So this question is asking whether the Turing machine satisfies P4, right? So that's what we are asking, right? So all these questions, whether the Turing machine satisfies this property or whether the language recognized by the Turing machines satisfies this property, they are all undecidable. That is Rice's theorem. Now what is P5? P5 is the set containing the empty language, right? So P5 is only one language is there in P5. It is the empty language. So it is the same. So here we are asking, maybe I'll use a different color just to stand out. Does the given Turing machine recognize the empty language? So then if it recognizes the empty language, it satisfies P5 because P5 contains only the empty language, right? So notice that here there is an empty set contained in a set. So the set containing only the empty set, where this empty set denotes the empty language, right? So this is a set of which languages satisfy this property. So only the empty language satisfies this property. P6 is the empty set. So notice the distinction between this and this. P5 is the set containing the empty language. P6 is the empty set, meaning the property itself is empty, meaning no language satisfies this property. So no language is contained in P6, right? So that is P6. So however, this is not going to be undecidable, okay? This is not undecidable. When I say this, I mean if given a Turing machine, it is not undecidable whether to check whether the language recognized satisfies P6, because we know that no language satisfies P6, right? So any Turing machine, we can say it does not satisfy P6 because whatever be the language it recognizes, it is not going to satisfy P6. So given a Turing machine, you just check that it is Turing machine and you can say it does not satisfy P6, right? So it's not undecidable. Anyway, so again, once again I want to highlight the difference between this and this. So P5 is the property that contains only one language, which is the empty language. P6 is the empty property itself, meaning no language satisfies this property, okay? So we say that a property is non-trivial, okay? if there is at least one language that satisfies that property, meaning that property is not empty, and two, the property is not all the Turing machine all the Turing recognizable languages, meaning, so two extremes. One is the property is empty, so P6 was the empty property, right? So that's a kind of trivial case. No language satisfies this, so we can say no Turing machine also satisfies this, right? So it's a trivial thing, so we don't even need to spend effort to check. Second is a set of all Turing recognizable languages. So given any Turing machine, it will recognize the language that it recognizes will be part of the set of all Turing recognizable languages. So that's also trivial. So between these two extremes, one is the empty property where no language satisfies this, and two is a set of all Turing recognizable languages satisfying this. Between these two extremes, any other property, right? So there are two things. One is that it must contain at least one language so that it is not empty. Two is that it should not contain all the Turing recognizable languages. So there should be at least one in the language and one out of the language. One Turing recognizable language that satisfies this property, and one Turing recognizable language that does not satisfy this property. If these two things are there, then it is said to be non-trivial, right? So I don't want the property to be all the Turing recognizable languages, or I don't want the property to be nothing also. Otherwise there is nothing interesting there, right? So we want not everything, not nothing. We want it to contain some language and it to not contain some language also, right? So it could be just one language that it is not containing, or one language is containing, that's okay, right? So all the properties that we listed here except P6 are non-trivial. So P6 is a trivial property because P6 is equal to empty, right? So P4, for instance, P4 is a set of all languages that contain 1011, right? So I can make a set of languages that are Turing recognizable, right? That contain 1011. You can easily make something, right? You can also make Turing recognizable languages that do not contain 1011, right? So you can have some other language, right? It's a set of all palindromes. It does not contain 1011, but it is Turing recognizable, right? And set of all strings that contain odd number of ones that contains 1011. So that is a Turing recognizable language that satisfies P4, right? So P4 is non-trivial. There is a Turing recognizable language that contains 1011, and there is Turing recognizable language that does not contain 1011. Another one is P5. What is P5? P5 is a set containing only the empty language, right? So empty language is there in P5, and any other language if you take, it is not there in P5. So set of all palindromes is not there in P5, right? Set of all, because P5 only contains the empty language, or set of the language is containing two strings 0 1, just two strings, that's also not there in P5, right? So P5 is also non-trivial. So all the properties listed here are non-trivial except P6. So this is not a non-trivial property, rather it's a trivial property. Right. So trivial properties are easy to check. Given a Turing machine, if it's an empty language, you can say it's certain empty property, you can say the language does not satisfy this, right? Okay. All Rice theorem says is that given a non-trivial property, right? So it could be any one of them, or it could be, there are many more that you can think of, right? P1 to P5, they're all non-trivial properties. Now consider the question PTM. Okay, so what is PTM? Given a Turing machine M, does M satisfy the property, or does the language recognized by M satisfy the property? Is that in P? Then PTM is undecidable. Given a Turing machine, it is undecidable to check whether the Turing machine satisfies this property, or the language recognized by the Turing machine satisfies this property, right? For any non-trivial property, that is Rice's theorem. So automatically last class whatever we did, like ETM is undecidable, regular TM is undecidable, both of them now immediately follow as consequences of Rice's theorem, because being empty is a property and being regular is another property. They are both non-trivial properties. So immediately by application of Rice's theorem, we know that ETM is undecidable and regular TM is undecidable. And now by whatever I have said, all of these questions that are asked here, does the language contain only strings of odd length? Does the language contain at least one palindrome? Does the language recognized by the Turing machine contain, let's say, 1011? All of these are undecidable questions, right? So Rice's theorem says that it is undecidable to check whether a given Turing machine satisfies a non-trivial property, right? Okay, so that is the significance, and that's the kind of explanation of what the statement of Rice's theorem is. So it's as you can think of, it's very, very powerful, right? Because not only did we prove that two already proven undecidable languages are undecidable, now I am saying a very huge set of languages, anything of this type, right? Any question that you can think of. Now, given a Turing machine, is the language recognized by this Turing machine, is it context free? Given a Turing machine, does it contain any string that ends in 000? Right? Does it recognize any string does it accept any string that ends in 000? Right? Given a Turing machine, does it recognize, let's say, two strings x and y such that x is the complement of y, right? So I can make any number of questions, and all of these are undecidable because they are all non-trivial properties. Okay, so given that, now let us move to the proof of Rice's theorem. Right? So the statement I have explained so far, the proof is also not that complicated. It's brief. It's interesting, right? It is by reduction from ATM, right? So ATM we have already seen. Given MW, we want to know whether M accepts W, right? So we'll show that ATM reduces to PTM, right? PTM is the property TM. Okay, so and this by results earlier shown implies that PTM is undecidable because ATM is undecidable. Okay, so by the statement of the theorem, P is a non-trivial property, which means it is not the empty property, and it is not the property of all the languages, all the Turing recognizable languages. Okay, so let's first assume that the empty language is not in P. So maybe I'll just write here, empty language is not in P. Okay, so it is so this is a without loss of generality assumption, right? So suppose empty language was in the property, right? So now what we are going to do is we can take the complement of this property. So when I say complement, I am talking about P complement. So when I say complement, what I mean is you take the set of all Turing recognizable languages minus this. So suppose this is P, suppose this is set of all Turing recognizable languages, right? So now if empty set is here, empty language is here, then we can consider P complement, meaning now asking whether a Turing machine has a property P and asking whether it has the property P complement is the same, because if it has the property P, it does not have the property P complement. If it has the property P complement, it does not have the property P. So to decide P is the same as deciding P complement, right? So PTM, so what I am saying is that we can consider P complement instead of P. So if P does not contain the empty language, we can consider P complement, and P complement certainly contains the empty language, right? And then proceed. And then deciding P complement is the same as deciding P. So it cannot be that PTM is decidable and P complement TM is undecidable, because they are like you just flip yes and no, the answer is the same. If you flip yes and no, the answer for PTM becomes the answer for P complement TM, right? So if PTM is undecidable, it follows that PTM is also undecidable, right? So it is enough to show that P complement TM is undecidable, right? So now because of this thing, we can without loss of generality. So again, WLOG stands for without loss of generality. Without loss of generality, we can assume that empty language is not in the property. Okay. So basically what we are doing is, we know that P is not the set of all Turing recognizable languages. We want something outside the language. So that we are picking to be the empty language. We also want something in the language, right? So that we are going to pick to be some language called, let's say, L0. So L0 is a language that is going to be in P. Okay. So L0 is going to be a language that is in P, and empty language is a language that is not in P. Okay. So now these two languages, the empty language and the L0, is going to be important in our proof, right? So we can assume that there is some language in the property, right? Because it is not the empty property, right? Because empty property is trivial, right? So let that be L0. L0 is in P, and since it's L0, which is a Turing recognizable language, let M0 be the Turing machine that recognizes L0. Okay, so we have the empty language not in P, and we have the language L0 in P, and L0 is recognized by some Turing machine called M0, right? So now we will make the reduction. The reduction is from ATM to PTM, right? From ATM to PTM. So given an ATM instance, meaning given M comma W, we will construct a PTM instance. So the PTM instance that we are going to be constructing is called M prime. Okay, this is M prime. Okay, so given an ATM instance, we are going to construct PTM instance. Okay, so let's see how to build the PTM instance from the ATM instance. So the reduction is very brief. It's not that much. It's very brief. It's what is written in the blue box here. Okay. So what does M prime do? So whenever it is given an input X, right, it runs or it simulates M on W. Okay. So where M prime has the ATM instance encoded in it. ATM instance M and W encoded in it. Sorry, M and W encoded in it. Right. So it runs M on W. Okay. So X is the input to M prime. M prime runs M on W. Okay. So not on X but on W. Now M may accept, reject, or loop on W. If M accepts W, right, so if M accepts W, then M prime starts simulating M0 on the input given to it, where M0 is this M0. It is a Turing machine that recognizes L0. Okay. So if M accepts W, then M prime runs M0 on X. So now is when the input of M prime is starting to get operated on. It runs M0 on X. If M prime rejects W, now if M rejects W, M prime rejects X, right? And if M loops on W, well, then it doesn't have to do anything. It just continues looping, right? So given the input, M prime simulates M on W. If M accepts, M prime further goes ahead and simulates M0 on X, right? And once this happens, when it simulates M0 on X, it will, whatever M0 does on X, it does. So if M0 accepts, it accepts. M prime accepts, right? So maybe I'll just note that here. And and basically whatever and does and accept reject as per M0. If M0 accepts X, M prime accepts X. If M0 rejects X, M prime rejects X. Right? Now, if that's if M accepts W. If M rejects W, then M prime rejects X. So let's see why this is a reduction. So now it is just a bunch of rules, but let's see why this is a valid reduction. So to understand this, we need to understand what happens. It's not that difficult. We just need to think what happens when M accepts W and what happens when M does not accept W. Right? These are the yes/no cases of M comma W being in ATM and not being in ATM. So let's see the first case. What happens when M accepts W? Right? That is the case. M comma W is a yes instance of ATM. M comma W is an ATM. This is same as M accepting W. In that case, when M accepts W, what M prime does is to simulate M0 on X. It simulates M0 on X and does whatever M0 does, right? So what is the language now recognized by M prime? So the set of strings recognized by set of strings accepted by M prime is the same as the set of strings accepted by M0, right? Because this condition is satisfied. So M prime is now simply kind of mirroring whatever M0 does. It does whatever M0 does. So the language of M prime is the same as the language of M0, right? So that's what I've written here. Language of M prime is the same as language of M0. But what is the language of M0? M0 was the Turing machine that was chosen such that it recognizes L0, which is a language that satisfies the property, right? So language recognized by M prime is L0, and we know that L0 is a language that satisfies the property, meaning that the language recognized by M prime satisfies the property, which means M prime satisfies the property, which means M prime is in PTM, right? So the answer to this question, right, does M prime satisfy the property P? The answer is yes, because the language it recognizes is L0, and L0 is a language that has a property. So if M comma W is in ATM, if M accepts W, then M prime has that property, right? So the yes instance of ATM maps to yes instance of PTM. Now we also want to see that no instance of ATM maps to no instance of PTM. Right. So in the case of yes instance, what happened is if M accepts W, M prime becomes a mirror of M0. Right. Everything is the same. But what happens if it's a no instance? Suppose M does not accept W. Right. So it could be reject, it could be loop. So in that case, if M rejects W, M prime simply rejects the input. Meaning if M rejects W, whatever be the input, it doesn't matter, M prime is going to reject it. And if M loops on W, then M prime doesn't even get to do anything. So even then M prime does not accept anything. So in either case, the input is not going to be accepted by the machine M prime. So which means the language recognized by M prime is the empty language. Right? So whatever be the input X, it's not going to accept that, because once M rejects W, M prime just rejects X. It doesn't depend on what X was. Right? So we are not doing anything more. If M loops on W also, because if M loops, it's just going to run M on W forever. It's never going to get to do anything on X. Right? So in either case, M prime is not going to accept the string X. So the language recognized by M prime is empty language. Right? And by our assumption, empty language does not have this property, right? And it was an assumption without loss of generality. So the language recognized by M prime is not in the property, so M prime is not in PTM. So this we have shown that no instance of ATM, if M does not accept W, results in no instance of PTM. Right? So both yes instance and no instance have been mapped, which means that MW is in ATM if and only if M prime is in PTM. So this means the correspondence of the reduction has been verified. And indeed this construction is a very fairly simple construction. Suppose once we are given M and M0, the rest is and W, we can just build this Turing machine. If I are given the descriptions of the Turing machines M and M0 and the string W, it's easy to build this. So the existence of the Turing machine M prime is not that difficult to see, and we have completed the correspondence, and that completes the proof. So we have a reduction from ATM to PTM, right? And that shows that since ATM is undecidable, PTM is also undecidable. Right? So considering how much we can do with this theorem, right? So it's saying that whatever may be the property, it is impossible or it's undecidable to check whether the Turing machine has that property, right? And you can apply any sort of non-trivial property to it. So considering how much useful or how much like broadly applicable this theorem is, the proof is actually not that hard. So when you consider that what we are getting out of this proof, it's not that much complex. Of course, it's like 3-4 lines, and there are like simulating 2 times of simulating going on, M on W and then M0 on X. But still, given how many kind of results we can derive from it or infer from it, it's actually not that difficult, or not considering that it's not that much of an effort, right? So that completes the lecture on Rice's theorem. So what is Rice's theorem? Given a Turing machine, it is undecidable to determine whether the language recognized by the Turing machine satisfies a certain non-trivial property. So given a Turing machine, it's undecidable to tell whether the language recognized by this Turing machine is the empty language, or the language recognized by this is a finite language, or the language recognized by this contains a certain string, or it contains only a certain type of strings, let's say only palindromes, or at least one palindrome, right? All these questions are undecidable, right? And it is important to have non-triviality, because if the property is a trivial property, like that no language satisfies, then, so for instance, the empty property, no language is going to satisfy this, right? So given any Turing machine, you can say it does not satisfy the empty property, because it recognizes some language, and that whatever be the language, it's not part of this property, because we know nothing is in this property, right? So it's a trivial, it's not undecidable to check whether the Turing machine satisfies as a trivial property. There are only two trivial properties. One is the empty property and the set of all Turing recognizable languages. So empty property is not satisfied by any Turing machine, whereas a set of all Turing recognizable languages is satisfied by all the Turing machines. So one is always no, one is always yes. Apart from this, any other property in between that excludes at least one language and includes at least one language, right? All of this is undecidable. So that is the proof of, that is Rice's theorem, and the proof was by reduction from ATM. So it involves this, and we explained that over detail, and that completes lecture 41, right? And in the next lecture we will see some other techniques for showing undecidability, and that's all for lecture 41. Thank you.